Have you ever tried to touch something accurately without looking, or steer a car in a straight line with your eyes closed? It is nearly impossible because you lack critical information. For robots, achieving precise actions and maintaining stability in dynamic environments presents a similar challenge, one they overcome with remarkable elegance. Robots use feedback for self-correction by continuously monitoring their actual state, comparing it to a desired state, and then generating an error signal that drives adjustments to their actions. This constant loop of sensing, comparing, and acting allows them to adapt and maintain performance even when unexpected events occur. The core mechanism behind this is the feedback loop itself, which typically involves three main components: sensors, a controller, and actuators. Sensors gather real-time data about the robot's current position, speed, or force. This data is then sent to a controller, which is the robot's brain, where it is compared against a predefined target or set point. If a difference or error is detected, the controller calculates the necessary corrective action. These corrective commands are then sent to the actuators, which are the motors or other mechanisms that execute the physical movement, bringing the robot closer to its desired state. In practice, this means a robotic arm trying to reach a specific coordinate will use joint encoders to measure its current angle. If an encoder reports an angle different from the target, the controller will send a signal to the motor to adjust the joint until the measured angle matches the desired one. Similarly, a mobile robot following a path uses wheel encoders and perhaps a camera or LiDAR to detect deviations, then adjusts motor speeds to steer back onto its intended trajectory. A gripper can use force sensors to ensure it applies just enough pressure to hold an object without crushing it, constantly adjusting its grip based on the feedback. This process is known as closed-loop control, a fundamental concept in robotics where the output of the system is fed back as an input to influence future actions. The effectiveness of this self-correction relies heavily on tuning parameters like proportional, integral, and derivative gains, often referred to as PID control. Properly tuned PID gains allow the robot to respond quickly to errors without overshooting its target or oscillating unstably. Ultimately, the ability of robots to use feedback for self-correction transforms them from simple programmed machines into resilient and intelligent agents. This continuous cycle of sensing and adapting is what allows robots to perform complex tasks with high precision, maintain stability, and operate reliably in the unpredictable real world, ensuring they can safely and efficiently achieve their objectives.
If you love robotics, like, subscribe, and keep building with us.